Hi, in this video we are trying to simulate the effect of gravity in this bar. So this is a solid steel bar with a diameter of 16 mm and the length of this rod is 1000 mm. So we have already defined the SPC in this location, which is nothing but constrained in all three DUFs as this is a solid elements. We only need to constrain the three DUFs 1 to 3, and then I'm just type Q again. Sorry. Yeah. So yeah, now I need to try to this we have constrained it, but we need some load also. So in the load section, we will create one more load collector here as a gravity load collector. If you press right click, go to create gravity, you can create it. This is a gravity card, and then in the gravity card you can just go to here. This is nothing but your coordinate system, so we are fine with this coordinate system. If our model is not in this coordinate system, we need to define in gravity in this direction, then we need to define a local coordinate system. But for this we are fine with our global coordinate system, so we don't need to even define the CID. This is coordinate system. Second is gravity. So what will be the value of gravity? As the MSC Nastran doesn't know the units, so it doesn't assume any gravity. So gravity, we all know that it is 9.81 meter per second square. But in MSC Nastran, we are defining here in current systems, we are defining in mms, newtons, and seconds. So that means we need to define our gravity in square, in per second square, which comes out to be 9810. And then we need to define the uh, downward direction gravity. Where is our model line? So here the gravity will act in the negative z direction. So this n3 is nothing but the negative z, is z axis. So we just need to define it as -1. So that is it. And then in the subcase again we need to call this gravity card in the load collector. So we'll go click on the load, and then we can just choose this one. Once this is done, we have already requested for the output request in the global card, and all other cards are set. So we can just go on here, and we can just go to file and export our model. So once this model is exported, then we can just go on here and solve it. So we can just go on here and solve it. And then once it is solved, we can just try to open this log file, and we can see this whether this is solved correctly or not. So this means this is solved. This is, at least it is solved, we can say. Now we can just try to open this OP2 file in our HyperView. So we have opened the OP2 file here, and then we can just plot the displacement. Displacements are coming very less here. This is the case of a self weight of this bar problem. The magnitude of displacement is maximum here and the minimum at the constrained location. And we can even plot the directional displacement. We can see like the x will be 0 here, will be nearly 0, and y should also be 0. This is due to the, maybe due to the Poisson's ratios effect, and this z will be the mostly the dominant one. So the z is the dominant one with the negative sign in here, and the positive is here, which needs to be 0. If you see here, the min and max. So if I can just go on here and go to this more degrees, or maybe I can switch to scientific one. So the minimum magnitude wise, the minimum displacement is here and maximum displacement is here. And so to check the mass, we can just go to this measure. In here, there is a one bottom icon. You can just press here and then just select this component as only one component is there. I will say compute, and it will throw one mass here. So which is nothing but 1.57 e raised power minus 3. Uh, so it is nothing but 1.5. This is in tons, by the way. So it is nothing but 1.57 kg. Now we got the mass of this bar as 1.57 kgs. So we also know the cross sectional and the length of this bar, which are these values. So from the mass we can calculate the weight, which is nothing out to be 15.4 something newtons. And if assume like instead of self weight problem, like um fixing the bar at the one end, and we are applying the load of the same as 15.4 uh, on the other end, and the gravity is not there, means the bar will feel like weightless. So what will be the stress? So stress will be nothing but like 15.4 divided by the area of cross section, which is coming out to be 0.077 MPa. And if we calculate the strain, which is nothing but stress divided by Young's modulus is nothing but 210 triple zero MPa. So we can divide this, and we from that we can calculate the displacement, which is nothing but strain into length. So we can get something like 3.68 e power minus 4. And displacement due to self weight will be half of the displacement due to the same load. So let's assume like let's calculate the half of this, which is nothing out to be 0.00184 mm, and which is almost the same as we are getting it here. So to derive this, we just need a uniform bar, and we have assumed the bar of length L, cross section A, and we are just taking like let us suppose like this is a very small element, cross section, that is dy, and which is y distance from the free end. So if rho is the weight density of the bar, which is nothing but weight by volume, so the total resisting force at dy will be rho into a times into y, which is nothing but the total force uh, acting on this small cross section dy. Then again, the stress in this small cross section dy will be nothing but the force by area, which is nothing but the total resisting force divided by the area of cross section. Area of cross section is same, so rho A into y divided by A, so it comes out to be rho into y. Now, if we need to be calculating the strain at this cross section, then it is nothing but the stress times the Young's modulus. So rho into y divided by E. And if we want to calculate the change in length of this dy, we just need to multiply this with the length of this cross section. So we have assume it is a dy which is very small, so we'll multiply this with this dy. And if we want to calculate the total length, the total change in length, then we just need to integrate it with the limits of 0 to L. So it comes out to be a rho al into L divided by 2ae, and rho al is nothing but rho is the weight density. So a cross L is nothing but the volume. So it coming out to be total weight. W is the total weight of this bar. So total weight divided into L divided by 2ae. So W is the weight of the bar, and this derivation is true for the prismatic bar, which means that uniform cross section bar. We know that if we seems to apply the W load and instead of this gravity load, then our total change in length will be WL divided by AE. We already know that. So this is half times of that change in length. One more thing is, so at the free end, there is no weight for the gravity to pull in. So the stress will be zero at this free end, and at the fixed end, this the gravity is having all the weight of W. So it is having W by A, and this curve will be linearly varying from zero to W by A. And if we apply the same load of weight of this bar to here, and we are not applying gravity load, then stress at every this cross section will be same as W by A. So we have calculated the value from the HyperView, and it is coming out to be 0.039 MPa exactly at the midspan, that is 500 mm from the free end. So if we calculate it via our formula, that is almost the same. And if you look closely, it is zero at the free end because there is no weight at the free end because we are applying gravity and there will be no resisting force at the free end. So that is stress at that free end will be zero.